Hello everybody, how's it going? It's Arnab here. Welcome to another CNCM lecture. Today, we'll be covering advanced applications of the Euclidean algorithm, as well as number theory functional equations. Now today's lecture will be more focused on problems, since the theory here is not too much. Instead, the lecture will contain more tips and tricks to solving problems of this nature. So, let's get into it. Okay, so let's start off by recalling the Euclidean algorithm. So it states that if we were to use the division algorithm to write A is equal to B times Q of 1 plus R of 1, then GCD of A and B is equal to the GCD of B and R of 1. So that would be Euclid's theorem. And then the Euclidean algorithm comes from applying this downwards, right? So then we can do R of 1 is equal to R of 2 times Q of 3 plus R of 3, and then you continue that chain downwards. So then we get that the GCD of B and R of 1 is equal to the GCD of R of 1 and R of 2, which is equal to the GCD of R of 2 and R of 3, etc. So then we come down to R of n minus 2 and R of n minus 1. So the GCD of those is still equal to GCD of A and B. And then finally, notice that our remainder is 0 over here. And you might be asking, how is the remainder going to be 0? Well, it has to become 0, right? Because these remainders are always decreasing. 0 is less than or equal to R of 1 less than B. R of 2 is less than R of 1. R of 3 is less than R of 2. So we keep going down. So R of n is less than R of n minus 1. So eventually, we're going to have to reach 0. So this is where we get it. That's what n represents. So over here, we have the GCD of R of n minus 1 is equal to the GCD of all these others. And then we could say, write it one more time, then that this is equal to the GCD of R of n and 0. So the GCD of R of n and 0 is equal to the rest of these, all of these. But the GCD of R of n and 0 is just R of n. So that means the GCD of A and B is equal to R of n. Right? So this encompasses Bazoot's theorem, which states that if A of 1, A of 2, all the way to A of n are integers such that their GCD is d, then for any integer k, there exists integers x1, x2, all the way to xn such that the sum over all I of A of I times x of I is equal to k times d. So essentially, all possible values of that sum is going to be the multiples of d, the integer multiples of d. And so if we were going to look at that for two variables, so just a of 1 and a of 2, in this case a is a of 1, b is a of 2, then the theorem sort of shows itself here because the easiest way to prove that theorem is to just show that the sum can be d, because then you can always scale the x of i's to get any possible multiple of d. So let's say we want to show that there is let's say we want to show that there's x1 and x2 such that ax1 plus bx2 equals the GCD. So let's say d, even though it's equal to R of n. So we want to show that there's x1 and x2. Well, this comes from the fact that we can trace all these remainders back to a and b. We can say that all these remainders are linear combinations of A and B. Why? Well, first, we know that we know that R of 2 or R1 is a linear combination of A and B, right? Because it's A times 1 minus B times Q of 1. So that's a linear combination of A and B. Then R of 2 is a linear combination of B and R of 1. But since R of 1 is a linear combination of A and B, it follows by arithmetic that R of 2 is also a linear combination of B and R of 1, or A and B. So that means by induction, say that R of 1, R of 2, R of 3, dot 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 to R of n. These are all linear combinations of A and B, so hence R of n is a linear combination of A and B, which is what we wanted. So that's Bazoot's theorem for two variables, and the theorem can be extended to multiple variables. But anyways, these are just prerequisites that you're probably familiar with. We're just giving a refresher. So the main tip here is, let's see, bounding. So the point is that we can, with the division algorithm, the Euclidean algorithm, we can bound all these remainders, or some of these remainders. We might not need all of them. We can bound these remainders and be able to degenerate a scenario or make some powerful simplifications. So in particular, an example is if we have, so let me come here. An example is where we have like this expression A divides B. And we know that there is a C equal to B plus K or plus MA, where M is just some integer. So C is equal to this quantity, and this quantity is something we know about. Like we can factor it, and we can bound those factors. So like if it's just some number that we have an easy deal handling with. So since A divides B and A divides A, that would mean A divides C. Now, if we manage to bound all these factors of C and prove that the absolute value of C is less than the absolute value of A, then we know that C is just equal to 0, right? Because the only way a number can divide a number with absolute value less than it is if that number is 0, right? So this type of trick is, while quite intuitive, pretty powerful in some situations. Another common thing is where um, you derive B from a Euclidean algorithm remainder, and then you divide out a common factor, and then you have another remainder, and then we can bound further on that one. So, hearing me say that out loud might sound complicated, but this example is going to help you make sense of it. So here's the problem. Find all triples x, a, b of positive integers such that x to the power of a plus x to the power of b plus 1 divides x to the a plus b minus 1. Okay? So first what we're going to do here is, so let's, since a and b are symmetric here, we can just deal with a less than b, right? And then we can deal with a equal to b at the end. But for now, we'll do a less than b. So, the first thing we want to do is get rid of this minus 1 on this side. Because it's just nasty. Like, maybe it wouldn't be so nasty if there was just one x term on the left-hand side. but here there's two x terms, so it would be helpful if we remove this minus 1 over here. And there's an easy way to do that. How? Well, basically as a consequence of the division algorithm, we know that um, x to the a plus x to the b plus 1 divides x to the a plus b minus 1 plus the left-hand side, right? So, in other words, it divides x to the a plus b plus x to the, x to the a plus x to the b. And we know this, not even by the division algorithm, it's just simple factoring because we know this thing divides that, so we can factor it out. This another factors this, so we can factor it out. So that means it divides the sum of these, right? So we have this thing, this left-hand quantity divides this right-hand quantity. So, give me a second. Um, Now what we want to do is notice that we have these x terms over here. So we can factor it out, and that would make life easier because, as I said before, we will end up with the new right-hand side, and maybe we can end up with some more insight from there. So what I'm saying is notice that x to the b divides all three terms on this right-hand side. Why? Because x to the b divides x to the a plus b. It divides x to the a because, oh, sorry, a is less than b, so it's the other way. So x to the a divides these three terms because it divides x to the a plus b, divides x to the a, and it divides x to the b because a is less than b. So we can factor out x to the a. Um, Actually, I don't need to rewrite that right now. We can do this thing, x to the a times x to the b plus x to the b minus a plus 1. Okay, so now we know that this divides that. But remember that x to the a, x to the a divides x to the a, x to the a divides x to the b, but then we have this one over here. So in light of that, we can use the Euclidean algorithm or Euclid's theorem, whatever you want to call it. We know that GCD of x to the a plus x to the b plus 1 and x to the a is equal to, so we can subtract out x to the a, which would mean GCD is equal to GCD of x of b plus 1 x to the a. And remember, this is not necessarily the remainder of this divided by x to the a, but we can still do this because as a consequence of the division algorithm, we can always subtract out multiples of this, and the GCD will stay the same. But anyways, now, as we said, x to the a divides x to the b. So again, we can subtract out these copies of x to the a from x to the b until it's 0 because x to the a divides x to the b. So then we end up with GCD of 1 and x of a, and that is just equal to 1. So what I've just said here is that this thing is relatively prime to the left-hand side. So what that means is that any factor of x to the a plus x to the b plus 1 can't divide x to the a, right? So it all has to divide x the other part of this right-hand side. So what that means is we can completely discard x of a and write let's see here, and we can write that x to the a plus x to the b is dividing x to the b plus x to the b minus a plus 1. So this is kind of nice, right? We already eliminated a factor like that. So basically, we know that we're doing stuff, right? We're not like going in circles or anything because we have something that looks kind of different from the original statement. Okay, so next, what are we going to do? We're going to do somewhat of a similar thing. We're going to subtract or add multiples of this left-hand side to the right-hand side to see what other things we can come up with. First of all, let's get a sense of how big these two things are. So we have this x to the b plus 1 here, x to the b plus 1 here. So hey, these two are actually pretty similar in form. The discrepancy here is x to the a and x to the b minus a. Now we don't necessarily know if b minus a is greater than a or less than a. So we can't make any conclusions here just yet. But what we can do to make life simpler is um, remove x to the b plus 1 from this right-hand side. And to do that, we simply subtract this left-hand side once. Okay, so what that means is we're going to do x to the a plus x to the b plus 1. And we're going to subtract that left-hand side from the right-hand side. And remember, that's allowed because, like we did in the first step, we could just add and the thing will still divide. So subtracting, same thing. So when we subtract, we get x to the b minus a minus x to the a. Alright. And that's better because now we can repeat the step we did over here by factoring out some x term. So all right, yeah. So once again, we know that x to the a is relatively prime with this left-hand side. So uh, uh, oh yeah, actually, sorry. We should do some cases. So first, if b minus a is greater than a, b minus a, I'll do a different color, greater than a. Um, yeah, so if b minus a is greater than a, then that means we can factor this right-hand side as uh, here, x to the a times x to the b minus 2a minus 1. So this left-hand side divides this thing. And since x to the a is relatively prime to this thing, we know as a consequence that x to the a plus x to the b plus 1 divides x to the b minus 2a. Okay, so at this point, we know that x to the b minus 2a divides, sorry, no. We know that this left-hand side divides this right-hand side, but b minus 2a is smaller than b. Okay, so that means x to the b minus 2a is less than x to the b. So on top of that, we have this x of a plus 1 term. So x to the b minus 2a is actually less than this whole thing. And we're even subtracting 1. So this whole thing is less than this whole thing. And so this is the example of the trick I was stating in the previous slide. I'm saying that because this thing is like, well, we know it's positive, and we know that it's way less than the left-hand side, we can conclude that it's equal to 0, right? So this means that x to the b minus 2a is equal to 1, which implies that x equals 1. Okay, so that's nifty. That's pretty nifty. But that's just one subcase. We need to consider everything. Okay, so let's deal with b minus a less than a. It should be pretty similar. So, okay. So, x to the a plus x to the b plus um, plus 1 divides x to the b minus a times 1 minus x to the 2a minus b. Okay? So, now as we did before, we can cross out the x to the b minus a. So now we have to deal with this thing over here. Remember that this is negative, so the absolute value of this is x to the 2a minus b minus 1. Now, 2a minus b is less than b because, as we said before, 2a is less than 2b, so 2a minus b is less than b. So as a result, the absolute value of this thing is going to be less than the left-hand side. So that means our right-hand side is equal to 0. Isn't that so cool? So x to the 2a minus b is going to be equal to 1. Hence, x equals 1. Which is nice. So that's just the a less than b case. Remember, we also did need to cover the a equals to b case. But, let's see. So we have, so if we like substitute a equals b into it, let's just work with a. Then we have 2x to the a plus 1 divides x to the 2a minus 1. And we're actually motivated to factor this right-hand side into x to the a minus 1 times x to the a plus 1. So difference of squares for the win, right? And the reason why we do this is because these two expressions look like the left-hand side. And so that means we could probably use the Euclidean algorithm to simplify things. And it turns out we can. So if we were to do GCD of the left-hand side with x to the a minus 1, or actually let's do x to the a plus 1 because that's actually easier. So GCD So if we subtract this once, then we get GCD, um, sorry, GCD, or we subtract it twice, sorry, because we want to remove this x to the a term on the left. So let's subtract x to the a plus 1 twice from it. So 2x to the a plus 1 minus 2x to the a plus 2. So that's negative 1 x to the a plus 1. And this is just going to be equal to 1. Like I mentioned, like you could just add x to the a plus 1 over here to get x to the a. So GCD of x to the a and 1. So you also get 1. But anyway, this is just me 1 because 1 divides both of these, and you don't have GCD that's negative. So what this means is that 2x to the a plus 1 and x to the a plus 1 are relatively prime, right? So any divisor of this will not divide this. Hence, we can cross it out. So now we work with the other thing, which is x to the a minus 1. So let's work it out. So once again, let's subtract it twice. The right from the left. So GCD 3 and x to the a minus 1. And so since it's the GCD of 3 and something, it can only be equal to 1 or 3. But since we cross out the x to the a plus 1, we know that 2 to the x to the a plus 1 divides x to the a minus 1. So that means the GCD of these two values has to be 2 to the x to the a plus 1. So that means 2 to the x to the a plus 1 is equal to either 1 or 3. So if it's equal to 1, so if 2x to the a plus 1 is equal to 1, then that means x is 0. So that would mean x is equal to 0, which is not in our solution set, right? Because x has to be positive. Or 2x to the a plus 1 equals 3, which means x to the a equals 1. So x equals 1. Alright. So, like I said, x equals 1 in this case. And if we go back, so notice that if x is equal to 1, then this expression will always hold regardless of what a and b are. So we did like end up finding some constraints, but it's no matter because any a and b is going to work. So the answer is, oopsies, let me move back to the original problem. All right, we assumed a less than b. This time will hold if a greater than b since this is symmetric. But anyways, our answer is 1 a b for any positive integers a and b. So that's example problem exhibiting the power of bounding with remainders, and as well as simplifying remainders and right hand sides, right? Because one, we removed these powers of x from the right hand sides, and two, we did bounding to resolve these cases, these subcases, so that we could reduce down to x equals 1. So that's the power of the Euclidean algorithm and just these number theoretical tricks in general. Okay, so let's go into our next topic, which has a slight bit of overlap with what we just covered. So this is divisibility functional equations, which generally is a field in which you have a function that's defined on some domain, right? And then you have a for all pairs of values, you have some sort of divisibility statement going on. So it's like a normal functional equation, except instead of equality, it's divisibility. So this is actually, you could say it's a large class of functional equations in that there's so much variability in what the functional equation looks like, but for a lot of these functional equations, the method to solving them is pretty much the same. And these are some heuristics that such methods involve. So one is to plug and chug to find trivial values. This is a natural step for any functional equation, right? But this is also something that is important for um, any divisibility statement, really, because you can use them to in maybe some sort of bounding argument or something. Yeah, they're just useful things to deal with. Next, try to find f of primes. So this is useful because now you have infinitely many values that you can then use in a bounding argument. And we'll see an example of this next, but basically, um, if a functional equation holds for, say all pairs of x, y, blah, 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 and you know the values of primes, then you can combine those primes uh, with normal values, fix the normal value, and then use those primes to work out some sort of argument. So yeah, we'll see that next. Next is something similar where sometimes you can find divisors of the left-hand side that are actually bigger than the right-hand side. So then you know that the right-hand side is less than the left-hand side. So then, like before, we would determine that the right-hand side is equal to 0. And this is useful because um, sometimes these expressions on the right-hand side, 1 equal to 0, they tell you a lot about the function. For example, look at this. If we had that p divides f of m minus m squared for all pairs p and m, like this is something we determined, then if we choose a large enough p, like, anything, if we anything that's bigger than f of m minus m squared, right? Because we fix m, so then we can choose any large p, um, and then that way you can't have this p dividing f of m minus m squared because it's just bigger. So this tells us that f of m minus m squared has to be equal to 0. That's the only possible value that p could divide. If you know for a fact that p is greater than f of m minus m squared. So then this means f of m is going to be equal to m squared. So this type of argument in which you choose an arbitrarily large p gives you some pretty important properties about the function. And usually, um, like this seems like a pretty intuitive idea, but sometimes it's maybe easy to miss, right? So I always try to keep in mind this um, strategy. And next is also sort of similar. See if you can find parameters or variables for the function that make the RHS right-hand side equal to a prime or square of prime or 2 times a prime, etc. Something that some simple function of a prime. Because this way, the left-hand side, if it divides this right-hand side, then that means there's only a small number of values that it can take, and then you can probably just easily consider each value, and then you can learn some important stuff. For example, if the RHS is a prime, then you know that the LHS will only be 1 or that prime. So it gives you a lot already. Okay, so here's our example. It's from the IMO shortlist of 2011, number theory, problem 3. So it goes like this. F is a function with domain integers, range integers, such that for all integers x and y, the difference f of x minus f of y divides x to the n minus y to the n, where n is a positive odd integer. Okay, so let's just write it up here so that we don't forget. So for all x and y in Z, we know f of x minus f of y divides x to the n minus y to the n. Okay, so um, the first thing we want to do is, as we said before, we want to find the trivial values. So like 0, 1, etc. So first, let's try finding 0, right? So let's see. If we plug in x equals 0, y equals 0, we get f of 0 minus f of 0 is divides 0 minus 0. So 0 divides 0. That's not really helpful. So we maybe just try having one of them be 0. So f of x minus f of 0 divides x to the n. Well, that's not too helpful, right? And it turns out anything we try to do in this direction, we can't find f of 0. However, there's something really important to notice. It's that if you have a working function f, then if you have the function f prime such that f prime x is equal to f of x plus d for all integers x, and d is just some integer, then it turns out this works, right? Because if we just try out f of prime of x minus f of prime of y is just the same as f of x minus f of y, because it's just shifting by d. So it means that if we find a function f, we already find like infinitely many other functions f. So that means that we can w log one value of f, so that in the end we can account for all possible values. But with this one function, we can just work based off of that. So what I'm saying is, let's just choose one value of x to define an f so that it fixes f. And so what we're looking for, we want an f of 0, right? So why don't we just set f of 0 to be 0? Because this makes things easy and nice, because now if we just like chose one to be if we chose one of these to be 0, then we already get some nice stuff, right? So let's look into that more. So we have f of 0 is equal to 0. Our natural next step is to try out 1, right? Or negative 1. Let's try 1 first. So now that we have f of 0, we want to try to involve that in some way. So let's try putting x equals 1 and y equals 0. That gives us f of 1 minus f of 0, which is just 0, divides 1. So what does this mean? It means that f of 1 is either 1 or negative 1. Remember that this is integer, so it can be either of these two. So what do we do here is um, we make another important observation about f. Notice that if f works, then negative f also works. Why? Well, it's easy to see, because f of x minus f of y, f of prime x minus f prime y is going to be negative fx plus fy, which is just the negative of f of x minus f of y. So that means that f prime x minus f prime y also has to divide x to the n minus y to the n, because its negative divides it, right? If the positive divides it, then the negative also has to divide it. So this means that we can choose another value once we've chosen, like we've already chosen f of 0 equals 0, but now we need to choose the sign of the function. So let's just, we need to use another value to determine the sign. So we can do that with 1. So we can choose f of 1 equals 1. Because f of 1 equaling negative 1 will basically do the same thing, but everything will be reversed. Everything will be negative. So yeah. So let's w log this. So now, great, we have two values of f. But now what do we do? So if we go back, some other tips were to involve things with primes. So if we do, let's try to first plug in a prime to this divisibility. Okay, so if we chose x to be some prime p and y to be 0, then we know that f of p divides p to the n. And so this tells us that f of p has to be a power of p. So f of p, and remember they can be negative too. So f of p can be plus or minus p to the k for some k less than or equal to n. Okay, interesting. But how do we continue from here? Well, we can also try to use 1. So if we do x equals p and y equals 1, then we have f of p minus 1 divides p to the n minus 1. So since we know that f of p can be one of these two values, let's try them out both. And we can always just assume fixed k and see which k do end up working. Okay, so over here, so if f of p is positive p to the power of k, then we have p to the k minus 1 divides p to the n minus 1. So we need p k less than or equal to n, because p to the k minus 1 divides p to the n minus 1 only when k divides n. This is one possible case. Now if instead f of p is negative p to the k, then we have negative p to the k. I should put bullet points there. So negative negative p to the k minus 1 divides p to the n minus 1. So this means p to the k plus 1 divides p to the n minus 1. And here's where we can use some Euclidean algorithm. Okay, so to do this, let's try to subtract this left-hand side a couple times from this right-hand side. Well, we know that p to the k times p to the n minus k is equal to p to the n. So we'll subtract the left-hand side, p to the n minus k times from p to the n minus 1. So this tells us that p to the k plus 1 divides, so minus p to the n minus p to the n minus k. So this would be p to the n minus k minus 1. Now, so we're basically in the same place again, except n was replaced with n minus k. So if we do the subtraction again, we'll end up with p to the k plus 1 divides p to the n minus 2k minus 1. So we could continue this downwards, right? Yeah, we can. So this means that we end up getting p to the k plus 1 divides p to the n mod k. Mod k minus 1. Now at this point, since we know that a remainder is less than its modulo, so that means that this thing is forced to be 0. So this means that k has to divide n. N equals mk. Then we have p to the k plus 1 divides p to the mk minus 1. But we also know that p to the k plus 1 divides p to the 2k minus 1. So let's say m was odd. So if m was odd, then we have that, so p to the mk minus 1 is a multiple, p to the mk minus 1 is a multiple of p to the k plus 1. But we also know that p to the m minus 1 times k minus 1 is a multiple of p to the k plus 1. Why? Well, that's because m minus 1 will then be even, And so p to the 2k minus 1 will end up dividing this. Okay, so that means p to the k plus 1 has to divide the difference of these two. Well, the difference of these two ends up being p to the mk minus 1 times p minus 1. Sorry, p to the k minus 1. However, note that p to the m times k minus 1 is relatively prime to p to the k plus 1 because we have this one thing and we can use the Euclidean algorithm. So this means that p to the k plus 1 has to divide p to the k minus 1, which is a contradiction. Thus, m can't be odd, so m has to be even. So this means that, in fact, 2k divides n. But this is a contradiction since n is odd. So we can rule out this entire case. I don't want to like completely scratch the work out, so let's just do that. Okay. So that was actually a lot for one subcase, but it's actually pretty close to being done now. So now we know that there's only one possibility for f of p because we ruled out this negative case. So f of p has to be p to the k minus 1, where k divides n. Now, how do we go from here? So what we do is basically another heuristic outlined on the previous slide, which is using a bounding argument. So let's choose some value x, okay? So let's choose some value x, or actually let's call it y, okay? So because that's just how we're gonna apply. So we're going to plug in x equals p and keep y. So now we have f of p minus f of y divides p to the n minus y to the n. F of p is equal to p to the k. Like let's just choose one p, which has its value of k. We don't yet know that for all primes p that the value of k is the same. So let's just choose one prime p for now, because we can't exactly generalize yet. So p to the k minus f of y divides this thing. It divides that thing, right? So also remember that this thing divides that. And why? That's because that's just follows by factoring, right? This divides that. So we know f of p minus f of y divides p to the n minus f of y to the n over k, but it also divides p to the n minus y to the n. So if we do subtraction, this means that p to the k minus f of y has to divide the difference of those two, which is y to the n minus f of y to the n over k. So here's where the size argument comes in. Now, we said we were going to choose one p. Well, let's choose some super large p, because if we fix y, then it follows that we can choose some p like super large, like go towards the direction of infinity. We can choose this p super large so that this left-hand side is bigger than the right-hand side, because we can definitely choose a value of p so that p to the k minus f of y is greater than y to the power of n. Even if y even if we don't know f of y, we can still choose a super large p. So this would mean that this is forced to be 0. So as a result, we got um, f of y to the power of n divided by k is equal to y to the n. So thus f of y equals y to the k. And this held for any y we chose. So that means we're done. But not quite. We still have to deal with the simplifications we made at the beginning. We can negate f, so we can do plus minus here. And also we can shift it. We can shift f, so we can apply this constant here, plus c. So this is a family of solutions. F of y is plus minus y to the k plus c for any uh, yn where k divides n. And obviously k has to be positive integer because it's in the exponent, right? Great, so that solves the problem. And it turns out there are lots of functional equations of this flavor where we end up finding f of p, and then we apply that, we choose another fixed y, and then we end up choosing super large p to give us what we want. There's lots of functional equations like that, so the tips we learned here will help you solve problems of that type. Alright, so we're coming to the end here now. So what we covered today didn't have too much theory. It was more of solving problems and gathering insights to solving problems in which you have these arbitrary divisibility conditions and you want to simplify them as much as possible. And to do this, we did a lot of Euclidean algorithm simplification as well as bounding. And there's an emphasis on bounding here. You really need to get a lot of practice with these bounds so you can easily tell when one expression is larger than the other so that divisibility can't happen. Usually it saves time and you can notice that right off the bat instead of proving something that might not even be true. So, in light of that, many of the problems of the day this week in the CNCM main server, they'll likely be related to the Euclidean algorithm and bounding. You might also see a couple of functional equations thrown in there, pretty similar to the one we just covered. So most of these will be on the proof side. Maybe it'll be a proof question, but computational answer extraction. So yeah, in summary, this is the type of thing we covered today. And yeah, so try to get as much practice with this type of problem as you can, because while these problems, tricks may have been something that seems super intuitive to you, when you get the practice, now it's like even more intuitive to you, and it's right in your toolbox. So you can like start applying these things pretty second nature. So yeah, thank you so much for watching. If you enjoyed this video, please make sure to leave a like and also hit that subscribe button if you want to keep seeing content like this. In addition, if you want to surround yourself with passionate math students just like you, go ahead and join the CNCM Discord server. There's tons of math-related discussion and activities that you can partake in that'll really, up your math ability. So here's the Discord server link. It'll probably be posted down in the description. You can find out more about CNCM at the CNCM main site, cncmmath.org. So yeah, I'm Arnav signing off for next time. See ya.